we're going to see the systematic bond graph generation for hydraulic systems. In here you're going to see here is a simple example that it has a couple of tanks, and it has a water outlet in here, and it has a valve in here, and it has a source of flow in here. What I would like to do today is the first step in a procedure consistent with what we have seen with the mechanical systems and also the electrical system would be to recognize the elements that make up the system here. And so we recognize the C element and the sources and the resistor over there. Okay. The second step, I am going to do something a little different now. Do you see the system is in blue here? Let's see if we get enough size in here that would be nice here. There we go. Maybe there. Okay. Step number 2, it says superimposing the construction of the bond graph on the physical system. And we need to lay the one junctions first for the distinct flows. So what I'm going to do is I am going to draw the actual bond graph model on top of the physical system, so that you can have a one-to-one relationship of the bond graph model and the elements and the components of the system. So you see in here, consistent with the procedure, the next step would be, as it's indicated in there, use a one junction to represent each distinct volume flow rate. So I am going to say, okay, look here, there is one. There is the volume flow rate in here. There is, of course, another one over here. And finally, one outside at the end, right here. So I put the one junctions on the system in there. And then I go to the next step. And again, we're superimposing on the system. Let me put the step here so that you can read it good. It says attach the one junctions, attach to the one junctions the physical elements that experience the distinct volume flow rates. This includes the sources and sinks, and I said note the activated bond on the right indicates that no pressure is exerted on the system at the discharge point. So in here I'm going to put an activated bond and source in here, which means a source with F = 0. So this is going to be our reference pressure here, so that's why we're doing that. So in here we put the valve in here, and the resistance and the inertia for this pipe over here, and the source over here. Any questions about this? You can see it's pretty obvious. We are laying out the physical elements in here that have a one-on-one correspondence with the bond graph model. Okay. Next step. Step number 3. We had, like on a mechanical system, to use zero junctions for the difference in velocities. On an electrical system was to use zero junction with difference in currents. Now here, zero junctions with difference in volume flow rates. So in this case, we say, okay, this is the one flow, and this is another flow. So the difference between this and this is going to be this flow. So it's very obvious that what comes in here minus what goes out through the pipe is what will remain in the tank, right? And it is the tank that sees this difference. Same thing on this right hand side. You see the difference between this flow and this one is what this is going to see. Actually, would be the difference between this and this. Yeah? So this minus this is what the tax is. So that is the third step. And let's take a look at the way I wrote it in there. So represent the difference between volume flow rates with zero junctions. And keep in mind the sign conventions, meaning what you consider to be bigger, to consider to be smaller, you know, in your sign convention to do this relative volume, what I would call. So this difference is we represented with one junctions. So this minus this is this. Now, the step number 5, it says attach those elements that experience those relative volume flow rates, and then those are also represented by one junctions. Do not worry about the bone numbers of causal marks at this point. You're just laying them out in here. And so we connect the R element, we connect the tank over here and the other tank over here. And lo and behold, we have the bone graft model finished in the laid out on top of the physical system, which provides us a one-to-one correspondence with the okay. Now, I said don't worry about the numbers and the causal marks at this point for only one reason, not because they are not important. In fact, we need to finish those bone graft models and the causal marks here, but what I was trying to say is that they are not necessary if you use CAMG, because as it is in here, the moment you enter it into the CAMG software, this is what you're going to have. See, check the power flow and directions and enter it into CAMG. At this point, the program will assign also the causal marks. So that is something that you can choose to do by hand, just to make sure things are okay and everything is okay with what you want to do. But you don't have to. I mean, you could enter the bone graft model into CAMG and have the CAMG software actually finish it for you. Any questions about this? There's a little more of an explanation here on this, so that perhaps we can take a look at this. Here I may say some observation for hydraulic systems. In this case, the first one junction represents the location where the flow is the same, but in fact this is also the summation of pressures, keeping mathematical consistency with the actual direction of the flows. Also consistent with the physics at the one junction, the sum of the pressures has to be equal to 0. The 0 junctions are the place where the pressure are the same, but the sum of the volume flow rates would be equal to 0. I have superimposed the bone graft model on the physical system so that you could directly relate to the bone graft model. And finally, a comment that I made is that this process is completely consistent with the same idea that we use for mechanical and electrical systems. Here's to have a common systematic procedure that establishes a systematic bone graft modeling generation process for mechatronic systems. In this case, this procedure, even if the elements are in different energy domains, would be helpful to generate much more complex systems. So the principle that has been established here allows models of very diverse nature or complex models to be built with the same procedure. And that is the point behind this explanation on relating it on a one-to-one the bond graph model to the physical elements. And so if you use consistently the same procedure for electrical, mechanical, and now for hydraulic systems, you can have a nice model here that would be ready for processing, going to MATLAB and getting the simulation done. Okay?